Hello. So I guess we are live. All right. So today the goal is to expand on what we built last time. So this is the series where we are going to build Llama-2 from scratch. We have last time built a baby representation of Llama. So it's a 100 million parameter model. And today we're going to expand on that model, make it better. And I think where we'll get the performance is with the attention mechanism, because the original attention mechanism, the multi-head attention mechanism, can be quite slow. So there are two interesting new research that have come, two methods. First is the grouped query and then multi-query. And I'll explain all about them in a few. So let's kind of just go through what we did last time, just so that everyone is on the same page. So we started off here that the goal is to build a 100 million parameter model, 250 and 500 million parameters. We defined the parameters of the model. So we have a number of layers, which is 6, number of attention heads, which is also 6. And keep in mind this number because it's gonna play a key role on the next stage when we are going to improve our attention. Then we have the dimensionality of the model, which is 768, and intermediate dimension, which is basically 768 times 4. And we set out to build the multi-headed attention mechanism. And we start off by building the scale.product attention, which is basically, here we're just defining the input, but that scale.product attention is just basically this much code. It's a function within our attention class, and here we just run our linear functions here, and then pass it on to the scale.product attention. And later on, we combine that into multi-headed attention, where we repeat that age times, right? So the idea of multi-head is having age multiplied multiple times, right? And we concatenate the results and pass it on to a linear layer, which, if we look at the image here, is exactly what is defined here. So we have this attention multiplied age times. We process all of them and then concatenate the results and pass it on to a linear layer. So far, so good. All right, so this is where we finished. Then we went on to build the rest of the network. So we built the multi-layer perceptron and the block size of the network, where we are pretty much, then we can stack up the attention, the layers of the network to build this model here. So first we have our embedding layer. We define positional embeddings as well, so that the model can know how the input is processed. And I think I should go deeper on this, but I'll go on this later. So here we just define the layers of the network and process it, create the model. We then went on to see how the model is, and we ended up with around 250 million parameter model. Now, let's make this better by focusing on attention. So what we built is this multi-headed attention. Each query, each key, and each value kind of match our one-to-one relationship. Now, what we want to do is compress that. And there's a lot of performance benefits, and I guess this paper describes them here. So you can see that the time it takes here's the multi-headed attention, right? It takes a lot more time compared to multi-query attention, right? Which is down here, to process samples. So you can have more samples per second. This is really good if you're training this large language models. This is an important thing, because you want to be able to process data without being too slow. If your system is too slow, no one will be able to properly use it. So here we have multi-query attention. It kind of performs linearly, but grouped query attention up to group, let's say 8, adds a little bit of latency, but not that much. It's not significant. It still performs like multi-query attention, depending on the number of groups you have. And you can see here now when you're the performance out of the box. So out of the box, you can see that multi-headed attention has great performance, but grouped query attention is not too far off. And with a little bit of fine tuning, you can get to that performance of the multi-headed attention. So this is like you could take an existing network and replace the multi-headed attention with, let's say, grouped query attention or multi-query attention and achieve similar performance. But grouped query attention performs significantly better than multi-query, so why not? Now, this is what you need to know about this. If you want to dive deeper into this paper, we can discuss later on. Perhaps we do like a group study somewhere where we go through this paper every single section, but I don't want to do that in this stream because here we are here to code. So, okay, we kind of know what this is. So let's set up to build it. So if you come back here to our multi-headed attention, we use this again here, right, in this block. But we can replace this, instead of multi-headed attention, we can replace it with grouped query attention. But let's first build multi-query attention and not grouped query, because actually all of them stack up on top of each other. So let's start. So we have here class multi-query attention. Attention. All right, so and then module, and basically we can copy this here and just replace the name here. Number of heads is not the same, because if we look at the paper, what the paper says about multi-query attention is that you have multiple queries that have only a single pair of keys and values. So per n queries, we have one pair of keys and values. So how do we define this programmatically? So we can start here by number of heads will be basically number of query heads or queue heads. Hidden dimension is okay. We can also do okay, embed dimension is hidden dimension, and then head of the dimension is just that divided by heads. So this still holds. Okay, so here we are gonna have self.query. This is gonna be an NNN linear layer, right? Because it's pretty much the same as attention. It's just that we are changing things a little bit. Do we have to go back all the way? I think we can. Yeah, I think we can do this here. Okay, so now we are gonna define the embed dimension and hidden dimension. So head of the dimension is gonna be, there we go, and hidden dimension is gonna be the first one. All right, so we have our queries. We can also define our keys now. So self dot keys is just basically a single pair of keys, but it's okay. We can just say key. They also have the same size, and we can go on to do the same for values. Okay. All right, so let me just see here. Okay, we still need the dot product, so we can also have that here. We could inherit, but I don't want to complicate things. I wanted to keep it clean. So we have the skill.product attention there. All right, so we need n queries. We need n times. Okay, so basically we could do a module list here, and then module list, and this is just going to be a list of linear layers there. There we go. Where we have 4 in range and Q heads. All right, so we have exactly one pair of queries per keys. So okay, that's correct. We want to process each. Okay, so forward. Let's go. So now we have our skill.product attention here, which is great. We want to be able to kind of do this, concatenate all of these values. So we're just gonna do a forward self. We take hidden state, and for this hidden state, X is going to be torch cat of first self.key query, yes. So this is gonna be the query, or not even query, it could be Q. We can call it Q because the query is gonna be, or queries in this case, not query, queries. So this is gonna be query on the hidden state. Okay. We also need the key, process the key. Okay. And we need the values as well. So this takes NKV. Okay, cool. So value, not values, value. All right. So we have here now kind of a draft of what this will look like. And this is going to be for query in queries, in self queries, right? Oh, okay. Awesome. No worries. Thank you for that. You can watch part 1 and then come to this one, or even better, if you can't come back to this one, you can also watch the recording and reach out to me if you have any doubts. So here we already have the scale.product attention, so we can just say self.scale.product attention, and I will show you something very interesting that you can do, which is basically just put all of these guys here. I think we need the mask, but we haven't added mask yet. I'll add that later. So we have here our skill.product attention that's applied to the each key and each query, key, and values for the duration of, for however many queries are there. And you'll get this final value here. This should be, okay, this is correct. So I just need to open this up this way. And then, okay, we already have that. And we are just gonna do, we need the output projection of this, do we? Oh, sorry. Oh, many tabs. Okay, so keys and queries. oops, what's happening with this mouse? Okay, cool. Each query goes to a group of keys and values. Okay, there we go. All right, so this is going to be, we're gonna pass it on to an output projection. Yep, because we're gonna get all of those values concatenated, so we still do need this. So let's add it here, and let's pass it to, let's return that. Okay, okay, cool. So this, let me just check the shapes. For that, I need to import everything. Start the environment. So let's see how this is going to behave. And it should be something like this, but for our multi-query attention. Oh, okay, we already have something here. So we can have here MQA instead of MHA, and we can have here multi-query attention, and this one I changed the name to multi-headed attention so that it's clear what is what. Oh, okay, I forgot self here. Self key, self value. Awesome. So, okay. Okay. So this goes here. Oop. Why is it getting it wrong? Didn't I? Okay. Yeah, it should be okay. Or did I embed dimensions? So yeah, this, we are just gonna call this the hidden state. We can call it embed, it's okay. All right. So I guess we can run this now. And let's see. We got an error, no module subclass. What do you mean? Did I miss any number of heads? Demodel, that's okay. Perhaps this. List is not a. Okay, I think it has something to do with this. Oh, typo. Okay, there we go. MHA. Oh, okay, it's multi-query. There we go. So, okay, Matt. Okay, the shapes don't match up. It could be, potentially. Where don't they match up? Okay, the output projection, for the output projection, they don't match up. And I say, oh, okay, makes sense. So this should be, the input for this should be times n heads, or NQ heads. Perhaps that should do it. Oh, okay. Oh, the features are more than before. Okay. So let's see. What am I getting wrong? Okay, so I had dimension. Oh, do the queries, do we embed the queries that way? Okay, so all of them take the same head. Okay, I was actually testing this yesterday on another notebook, so let's see what I potentially got wrong. Here it was working perfectly, so let's see. Module list, embed queries, so embed dimension times and number of queries, of course. And queries. Oh, okay. I guess I see. It's actually a tiny bug. It's actually a very tiny bug, and that's because I'm not aggregating all of this in the last dimension. So if I do that, oops, not this one. I don't want this one. Clear output. Oh, still? Let's see. So embed in the last dimension, embed queries. Okay. Okay, that makes sense. But I don't see, oh, okay. Okay. So perhaps I need to separate these K, V, and let's see what we will get exactly. We're computing these at real time or at runtime, so we can just have these V and K here. So this should output, okay, so let's see. Still remains the same. Oh, no. It should be this times this. So let's see now. Exactly. So there was a problem here because I was actually not respecting this head dimension here, which is kind of what we are compressing or expanding our, in this case, we are compressing our vectors into this kind of shape. So we needed to kind of expand that here in the output side. So if we look at this, and also multi-query attention should work. Attention head is not defined. Okay, so let's see what is missing. Oh, okay, I didn't define attention head. So now that that's defined, you will see that we do have an identical shape for multi-query and multi-headed attention, but of course this one here would, multi-query would work much faster than multi-headed attention, especially if you scale the number of data points, or let's say sequence length. Okay, so now we've implemented one. Let's go on to implement the last one, which is grouped query attention, before we move on. So the idea of grouped, I can just copy this and replace it here. Okay, so the idea of grouped is that we have we have here in the paper, so we have a group of queries, let's say 2 queries that match up to one key pair of keys and values. So it doesn't have to be 2. You can have n queries that match up to a single pair of keys and values. So you take the idea of multi-query and you match it up with the idea of multi-headed, and you kind of have the hybrid of that is grouped query attention. And to implement this is actually quite easy, because we already have our multi-query attention here. We can easily just piggyback on that and define these things. So let's go into it. Multi-query, this is going to be grouped query attention. And okay, so we do have n number of heads. We now also need a number of k v heads, because you also you want to define number of queries that you're gonna have, and how many queries, groups of queries are gonna match up to keys and values. So here we have these. We're gonna have self and key and key heads. Okay, that's gonna match up to these, and we're gonna have that's gonna match up to these guys. We have dimensions that we want, but do we care about them right now? Yeah, we might need to use them later on. So we're gonna define, and of course, one thing I have to mention is that this implementation is the simplest one. It's just for kind of to showcase, and also it works. But if you wanted to do this in a more efficient way, you might want to not use loops, avoid loops in general, and just kind of shape your tensors in a way that you can extract this information easy. And I guess the implementation that's pretty neat on this is in the transformers library. If you go to any of their models, including like the Llama and let's say Llama and other models, they implement it this way. So instead of calculating, let's say, doing a for loop on the number of heads, let me just get this back to view. Instead of doing a for loop in the number of heads, the way we presented earlier, let me see if I can zoom in. Okay, let me crop this out. So instead of doing a for loop as we did, you just kind of create a vector that projects into a bigger space, like number of heads, GitHub, number of heads times that dimension, and later on you can extract the n groups of k, or just n k's if you're doing either grouped query attention or multi-query attention. This is a much faster way, and you save compute this way. But I'm showing you kind of the simplest way to get started with this, and later if you want to do a more complex implementation, go ahead. I would love to see how you guys work with this. Okay, so hidden dimension, getting back to it. So here we have our hidden dimension, and okay, so now we have these. We want to create groups, and basically the groups are number of heads. Okay, the groups, exactly. So n, you define that by n and groups, nk groups. How did I define it? Let's see, because I already did this and trying to recollect from memory. Okay, so we have number of key value heads, that's here, that determines and grouped is just okay. All right. All right. All right. I guess we can just copy this. It's already here. We can reuse this. Okay. Self-grouped, number of key value heads is just nkv heads that we need to replace, and query for each group. Let's see. Number of queries per group. Okay, so number of query heads per group. We can define that here. Per group. And we can replace this thing here. Okay. Number of key value heads is just replaced by this. All right. We are not annotating at the moment. Mask is just none. And yes, of course it's a tensor, but we don't have to do that right now. And we change this to hidden state. Hidden state. Okay. All right. So what's happening here? A couple of things. First, we are piggybacking our existing class, which is the multi-query attention class. And what we are doing is that we are generating nkview heads. So let's say you need only 2 groups of k. You define them here, right? You repeat this 2 times. If you repeat this n times, you're gonna get nkv heads. So basically this bigger loop here is creating these values here. So these individual values here. And then n queries is defining how many queries are matching up to each group of kv values. So basically that's it. Here we have nkv, hidden dimension, that works. Intermediate dimension, that is basically defined earlier. We can just define it here. Self intermediate. What value do I have? Hidden dimension. Oh, okay. It's already defined inside, so I really don't need to define this anymore because I already had defined explicitly here. Of course, it's just a simple calculation, but you can pass it on also as an argument. So that's it. Also, it just looks better if you do it that way, not the way we're doing it right now. Right now, we are hacking a solution together. Okay, so we have this, and we can just copy this and call this GQA and just change the multi to group or grouped. Let's put here, let's rename this to grouped query attention. Oh, okay. There we go. And didn't take a hidden dimension. Oh, okay. So wait. So it takes number of queries per here. We want to have number of queries per group. We want to have 2 queries per group, as it was defined in the paper we just saw. Number of kv heads. We can. Okay, so if we want to have 2, actually we can just define here number of query heads are gonna be let's say 24. And if we want each to have, and we can define here as 2. And hidden dimension is just gonna be the model. That should work. Okay. Am I missing? Okay, no, I'm not missing anything. This is just follows a keyword. Oh, okay. Hidden dimension. Got end query. Oh. Doesn't take end queries. Okay, it's not end queries, it's just end heads. So what is now NQ heads got multiple. Oh, okay, so NQ heads is first, so that's why we don't pass that there, and then is the dimension. So this should be fixed now. And it's also hidden dimension? Yes. So hidden dimension. Okay, so we should be on track. There we go. It's working. So what does this mean actually when it comes to this? Let's extrapolate the values here. So let's first print out this ZX. So if we do print ZS, you're gonna see what we will get back. And wait. It's not printing out. Okay. Oh, okay. I'm running the wrong thing here. Oh, okay. So now we're getting an error. Multi-query attention takes 2 positions, but 3 were given. Takes 2. Oh, okay. We don't pass the mask and here. Yep. All right, actually we don't need to see the value, we want to see the shape. Okay, so we can see here that we get 1500 as our last dimension. And if we examine this further, what happened is at the group query level, you'll be able to see, actually, I think it will be clearer if I just do this. So if I print K shape, you'll see how many times K was repeated, which also kind of equals to how many times it was concatenated. So if you look here, except this last one, except the last one, these are the values of K. So K was repeated 2 times, right? You can see here the first time and the second time, and what was the dimension it had. And it's the same thing for V. So V was repeated 2 times, which means we have 24 queries, which actually equals to around 12 NQA heads per group. This should be not 24 but 12, because this value, I was actually testing this yesterday, this value here, let's copy this. I was trying to illustrate this point, but I got lost here. Okay, there we go. So we have number of heads, of query heads, and number of let's see, queries per group, or in this case would be the way it was defined. And this value here is actually supposed to be 2. Okay. So basically it's gonna be, we're gonna have 24 heads in total, meaning every 12 heads will have a single pair of KV. Now, the way this is implemented, like when you're multiplying this as a tensor, is as if you are repeating. Let's say in the 12 heads, you have each two query heads have a single value of k, but that value of k is repeated a few times. To be more precise, you have, in our example, we generate two pairs of keys and values, and since we have pretty much 24 query heads, each 2 queries has a pair, because we repeat this value around 12 times if you really go into like the tensor side of things. And I demonstrated this, I tested this out in the example I was testing out yesterday. So here we have a normal example, the same as you saw, but if you go, I was looking at the StarCoder paper and how they implemented this, and I looked at, they have 24 query heads, right? And each query head has a single, or there are 2 heads of KV. And what they do later on is that they use this repeat KV that, let's see, let me go to that part in particular. So they repeat the KV values here, and if I printed the states before and the states after so that you can see what I mean. So the states before, you can see that there are only 2 values of k, meaning k is repeated twice as is specified as number of keys and heads. But then when they repeat the value, when they do the repeat of kv, you can see that it kind of ends up at 24, meaning every because they're doing kind of dot product, so meaning every 2 queries has a single key, although that key is repeated. So this is something you can try out and look at the code, inspect line by line. It's something I would definitely advise you to kind of test out. Let me just remove this print statements. I think the point is across. If you have any doubts, just feel free to reach out. Now here we have that's the same thing, should be 12. It will should still work exactly. So it should still give you the same shape as initially, but of course now it went through attention, meaning there is some processing that happened behind the scenes. And these 2, grouped query and multi-query attention, are much faster than multi-headed attention. And we will see this when we start training these models and we can test them out and see how they perform when they are training. And that I think next step from here is to go to creating the data set, processing it, and then start the training, at least for one of them or 2 in parallel. We will see what we can do. And if you just build up this model, or we can, let's say, we can now replace this with either grouped query or multi-query attention. I think for multi-query attention, it should be quite straightforward. So let's do that now. So we can replace this with MQA. We already run this. This should run without a hitch. Here, it should also run without a hitch. Exactly. And then we come on here. What I didn't specify here is that group query attention requires, like if you're doing stuff like that, you might need to use rotary positional embeddings instead of fixed, but that's okay. We can work on that on the next stream and then proceed on to create, start training the model after we process the data set. Here we have the model that we generated last time. It should be around 250 million parameters or 100. I forgot how many parameters exactly. Oh, actually, you can see now that we reduced from 257 with multi-query attention. We actually have around 20 million less parameters, which is great. And if you go with the vectorized implementation of this, we can actually bring the number of the parameter count even further down. So yeah, that's it from today's stream. Next stream, we will work on rotary positional embeddings, and we will start with the data set and then move on to training. So that's it. Bye-bye.